Hello, ladies and gentlemen. Welcome to a little corner of the internet called Marshable Math. My name is Mr. Marsh. Today's lesson is going to be on function operations and composition functions. So if you get yourself a piece of paper and a pencil, we will jump right in. A couple terms to remember that you need to know. Remember your basic input and output quantities. Input is what you put into the equation. Output is what you would get out as the results. Remember that a function, though, is a relationship in which there is only one output for each input. So every time you have a duplicate input, you should be getting the same output back out. If not, then it's not a function. Remember domain and range. Domain would be your allowable inputs. Range would be your allowable outputs. And function notation. Function notation is a slightly different way of writing equations and inputs and outputs. Usually we call the input x, we call the output y, but function notation says the input is x, but the output is f of x, right? The function of x. Okay, so let's consider these two functions right here. I've got f of x, which is my y value if you want to. Okay, it's a function that I'm going to name f just to keep it separate from g over here. And it says I'm going to take the input and triple it and then subtract 2. The g function, which tells me my input is x, says I'm going to take the input and square it and then add 1. Now remember your basic math operations of add, subtract, multiply, and divide. You're used to doing those with numbers. Now we're going to do those operations on the functions themselves. So let's see here. We've got number 1. Let's do f of x plus g of x. Then number 2, let's do f of x minus g of x. Number 3, we'll do f of x times g of x. And then last but not least, number 4, we'll do f of x divided by g of x. Now these are all pretty straightforward. All we're really doing here is asking you to add, subtract, multiply, and divide. So press pause on the video and see what you get when you add, subtract, multiply, and divide these equations. Go for it. Okay, are you done? Well, let's see here. All we're going to do is we're going to take the function called f and add it to the function called g. So in an effort to help you follow here, let's color coordinate it. We're going to do a 3x minus 2, and we're going to then add that to the g function. G's in red, x squared plus 1. Okay? Add up your like terms, put it in standard form. Let's see what I've got in the end. Wouldn't that equal x squared plus 3x minus 1? Okay? Simple enough, right? Okay? F of x minus g of x. Now, watch this here. This is going to be a little bit different. This is going to be 3x minus 2, but I'm subtracting the group, right? So it's minus now, but it's minus the group. So let me really put parentheses around here so that you can see that it's minus the group. X squared plus 1. It's minus the quantity. Now remember, when you have something that's set up like this where it's minus the group, you have to distribute the negative. Okay, so the first step here would actually be to distribute this negative, and since I got some room here, I'm going to work down. It would be 3x minus 2 minus x squared, and then minus 1. So in the end, I would get a negative x squared plus 3x minus 2 minus 1 minus 3. Okay, that would be my answer to this one. And notice order would make a difference here. If we took g minus this group, we would be distributing the negative on the blue here. When you added it, it didn't really matter. Okay, this one here, the multiplication is just going to be like probably what you've done before. 3x minus 2, and you're going to multiply it by x squared plus 1. You've done stuff like this, but you didn't realize you were doing a function operation on it, but you were. Okay, so 3x times x squared is going to be equal to 3x cubed. 3x times positive 1 is going to be plus 3x. Now distribute the negative 2. Negative 2 times x, negative 2x. And then, what have we got here? Oops, missed the square on that one. Negative 2 times 1 is negative 2. And then you collect your like terms. You see where that one's going. This one's a little interesting though. I hate that sign, hate the division sign. We're going to use a fraction bar, okay? So what it means is f of x, which is 3x minus 2, divided now by the g of x, x squared plus 1. And of course, order would matter on this one. But there's an interesting thing here. I really can't simplify that anymore. But if my denominator were 0, I would have to make an exception in my domain, right? There's no value that I can't put into x squared plus 1, but there might be a possible value that would make the denominator 0 in this case. Now, not in this particular case, because whatever I square here, my denominator is always going to be greater than 0. It's never going to be 0 or less than 0. But what if I had g of x divided by f of x, right? F of x is going to have in the bottom 3x minus 2. There's a number here that I can put in for x that would make my denominator 0, and I would have to exclude it. I would have to say x can't be equal to, you know what it is? 2/3. 2/3. 2/3 was allowed up here, but 2/3 is not allowed when you do the division because it would make the denominator 0. Okay? So that would be a domain restriction. All right, now these are all pretty simple and, in my opinion, kind of boring. Let's do something else. Let's do the composition function. A composition is when you put some things together. So now let's put some things together here. Perhaps you've seen this written out somewhere. Perhaps you've seen F and then a circle and then a G and then something like that. So it says like fog. It's really not an O. It's just it's an open dot. Or maybe you've seen it like this. F parentheses G parentheses X. Close, close. This is the one that I kind of prefer, because what you see here is that the input for the function f, the outer parentheses, the input for the function f is actually not just the number, it's the expression of g. So you're putting a function inside a function, so to speak. You say, what? Well, follow me on this. Let's actually use some numbers. Let's do f of g of 2. Okay? Now, what this is saying is that I'm going to use my input for f, whatever my output of g of 2 is. So what's g of 2? G of 2 is equal to 2 squared plus 1. G of 2 is equal to, what is it? 5, right? So I'm replacing g of 2 with what it is. It's f of 5. Well, what is f of 5? Well, I'm going to say, all right, f of 5 is equal to 3 times 5 minus 2. F of 5 is equal to, what, 13? Okay, do you follow what happened? I used an input of 2 in this function, and I got an output of 5. And then I took that as an output and used it as an input for the outer function and ran it through. So I'm kind of daisy chaining these functions together. I'm taking the first set, input, giving me an output. Then I'm taking that output and using it as the input for the next one in line. Okay? We can actually do that without numbers. Watch me on this one. Let me do this in color here now. F of g of x, which is f, 3x minus 2. So 3 times an input minus 2. What's my input? X squared plus 1. If I simplify this all together now, I'm going to get 3x squared times 3 minus 2, right? So that would be what? A plus 1? Now what do I get if I do a 2 as an input for this? 3 times 2 squared plus 1. 2 squared, 4 times 3 is 12, plus 1. Goodness. I get one equation that will do this. Instead of taking it in 2 steps, I get one expression that will do this in just one step. Okay? That's kind of cool. Yo, dog, we heard you like functions, so we put a function in your function so you can function while you function. I'm sorry, nobody watches that show. At least no decent people. Question for you. This is f of g of x. What if I did g of f of x? Does order matter when you do this? When you do composition functions, does it matter which is the inner function and which is the outer function? Which one you put into the other one? Give that a shot and see what you think, okay? I hope you learned something, and I hope you have a great day. I'll see you next time.